Welcome to another episode of Mathematics Visually Explained. With this episode, we start a journey to machine learning or deep learning, beginning with our first building blocks, a linear regression model optimized by stochastic gradient descent with the least square error objective function. More will follow, such as normalization, objective functions, regularization, deep learning, and so on. We start this video series with a step-by-step visualization of finding the best linear regression line using stochastic gradient descent optimization on minimizing the squared distance of each point, which is a so-called least squares method. Here is a quick preview of what you're going to see. Keep in mind, this is a sped up version. You can skip this and see a slower version with our guidance at the end of the video. You could ask, why do we start with this part? By the way, if you want to skip the explanation, you can skip to the animation part of the video. Well, because everything from what we call machine learning, deep learning, or AI has been built from these building blocks over the years. Let me show you. Here is an oversimplified timeline and layout how neural networks are evolved from where they are now. As I said, this is really simplified. We could talk for hours about the topic and could warrant its own Netflix series. So, regression came along with Legendre and Gauss. Perceptron follows, which is a simple classification layer. Then Adeline is the first one-layer neural network with a least square objective function optimized by stochastic gradient descent. In fact, in 1962, Madeline was already a three-layer neural network. Building on these ideas, among others, LeNet was the first convolutional neural network that has been used for reading handwritten digits at AT&T. Research speeds up from here, as computational power grew and the potential of the GPUs was recognized as the perfect tool for multiplying vectors together. Neural networks took over the lead in all image processing and high dimensionality tasks. Nowadays, deep learning is applied in computer vision and big data problems all over the spectrum. And this is the main focus of today's video, to understand the building blocks of deep learning. Building on linear regression with least square objective from Legendre and Gauss. Optimized with SGD or stochastic gradient descent, which basically means a step-by-step adjustment of the slope and intercept. This has been used since 1960, starting with Adeline, as short for adaptive linear neuron or later adaptive linear element. As the name suggests, it was used for optimizing a single-layer neural network or a linear regression problem. And here we are, stacking this with more layers in various ways you can build neural networks and apply it in your projects. Now, let's visualize how we optimize a linear regression model with stochastic gradient descent and squared error objective function. For demonstration purposes, we only took 8 points from the King County housing dataset. I link this in the video description below. We selected square meter as our input parameter. The reason you see the axis values between 0 and 1 is that without normalization, we won't be able to find the regression line. The same applies for deep learning. Our weights, in this case slope and intercept parameters, just won't be able to work with a predetermined learning rate. So eventually, they just blow up. But we will cover this in our next video. Right, let's get back to our output value y, which is a price we try to infer based on the square meter. How do we achieve that? With stochastic gradient descent, which is a step-by-step optimization process you can follow and understand. In the upcoming animation, you will see the complete process iterating over the 8 points until we arrive at an optimal solution at the bottom of our gradient valley. The slope basically tells us the relationship or change of price over the change of square meters, meaning dy per dx. The price is relative to the square meters. You can observe that the slope will slowly get steeper while reaching the optimum solution. The intercept basically gives us the price of the plot value or a 0 square meter house. It's slightly more complicated than that because we disregard all other variables, but it's a good intuitive way to remember. You can observe that the intercept decreases over time by reaching the optimal value. We define the error by the difference of predicted value and real value, whose square we try to optimize. This is called the squared error objective, or loss function. In our next video, we'll address mean square error and absolute error objective. Lastly, you can see how we optimize our slope and intercept.
So, let's look back. What were all these keywords? The linear regression line just shows the relationship between the price of the house and square meters. This relationship we try to find by looking at the difference of our current model and the data we have. Specifically, we nudge our slope and intercept parameters relative to the error. The nudges are deducted from the square error and moved by the gradient descent. You can see these zigzags, which are the individual optimization nudges. They will be smoothened by using a mean objective function with gradient descent in batches. Let's look at our slope. You see how the slope gets steeper over time and how the intercept decreases. So does the error. You can also see that on the red background chart on the right side.